Okay, welcome to Lightning Talks. The next presentation will be by Orestes. He has 15 minutes. Have fun.
Thank you very much. Good afternoon. I'm very happy today because it's my first time at FOSDEM, so let me introduce myself a bit. My name is Orestes Mas. I'm a professor at the Polytechnic University of Catalonia, where I teach mainly linear circuits and systems. And I have a problem. The problem is I need to draw circuits, lots of them, to be included in all sorts of documents, exams, articles, and so on, mixed with other kind of graphics, with function plots also, and with mathematical formulas and symbols. So you get the idea. So, but these circuits cannot be drawn in whatever way. Instead, have to fulfill certain restrictions, which are more or less these ones. First of all, they have to be beautiful, of publishing quality. We need a large library of predefined symbols to avoid reinventing the wheel over and over. And it's better to not mix libraries from different authors, because you will end up with a mess of styles. We also need to change the appearance of symbols upon needs. And a thing I consider very important is a consistent typography between the text and the graphics. For instance, here you have a circuit where you have some symbols over there, variables, currents, voltages, and often you makes reference to these symbols in the text. And if you look at the symbols, they have a font. And if you later change your mind and want to change the font, the graphic has to change the font too. For instance, here you have other kind of symbols, and the graphic is updated accordingly. And finally, we want to create and edit these graphics, these circuits, using free tools on free systems and saving it in free formats. So obviously there are many software packages out there to draw circuits, but if you apply those restrictions, the list starts to shrink. So we ended by choosing, first of all, LaTeX, to write a document in LaTeX for the great quality it provides. And second, describe the diagrams textually in TXZ, which is a subset of an extension of the LaTeX language. So with this method, we achieve perfect integration between text and graphics. We gain programmability and flexibility. Maths are no problem because you have all the LaTeX power to typeset math. Also, TXZ has a root library to typeset circuit elements, which is called Circuit TXZ. And we end up with vector graphics that you can enlarge and shrink without loss of quality. Here you have an example. In few lines, you can describe a graphic, which is useless in this case, obviously, but you more or less see the power of the solution. Okay. Is that the end of the story? Not at all, because the Circuit TXZ is a good choice, but for us has some minor issues. Aesthetical ones and also practical ones. When you write a circuit in TXZ, you end up in Circuit TXZ, you end up specifying absolute coordinates all the time, and this is not very good. Also, if you look at the graphic on the right, you see that this other graphic is more consistent, with the line width is more consistent. The elements are better proportionate, and the syntax here you don't have the syntax, but it's clearer in some ways. So we decided to use a thing called circuit macros, which I described a bit later. So what's PyCirkuit? PyCirkuit Obviously, when you describe a circuit textually, you need some sort of visual feedback, and PyCirkuit is an application that has in the background some compilation steps and presents the result to you in a visual form. It's an application written in Python 3, and using PyQt 5, so it works in Windows, Linux, and Mac. It's multi-platform and has two modes of operation. Here is the graphical user interface mode, and also has a command line interface to process files in batch mode. How it works. First step is to describe your circuit diagram in a source file. And in the source file, you put the elements using a circuit macros, which are a set of macros written by Dr. Appelwich of the Waterloo University in Canada. And then you use the M4 utility, the GNU M4 utility, to process this source file and expand the macros into PIC language. PIC language, unfortunately, is not understood directly by LaTeX, so you need another step, which is done by the PIC utility that it's also written by Dr. Appelwich. And the PIC utility converts the source, in this case the PIC source file, into various languages, which some of them are generic and some of them are LaTeX specific. We chose, for our purposes, the first one. So here we have the two steps I mentioned earlier are here depicted in FOSDEM violet color, and you end up with a TXZ file, which you can embed this in a minimal LaTeX document, process it to obtain a PDF file, and then this PDF file process it again to obtain a raster file, a PNG file in this case, to visualize it. So, as a bonus, at the user request, we can also generate other formats like SVG, JPEG, etc. So this is the whole picture essentially. Now the PyCircuit is in Debian testing, so Debian testing user can install it pretty straightforward. If you don't have Debian testing or you have other operating systems, you can use PyPy or pip install to install it in your computer, and the sources are on GitHub. If you install it by hand, you have to install other dependencies. You can see the README file to see it. So let's do a little demonstration. Here you have the graphical user interface, and you can start to enter the code here. This is a minimal template that the PyCircuit offers when it starts. So we start with a source, in the upper direction. You can parameterize it with various symbols. Here you have, for instance, in the documentation, you have all the possibilities for the source element. It's very well documented, the circuit macros. So you can change, for instance, in this case, to a square wave. We can apply a label. In this case, the label is a left label because going up, the label is in your left hand, and it accepts three parameters, A, B, C, that goes into the bottom, center, and upper position. So you can change that to the symbols to specify the voltage. Now we are at the top of this source, so we can add other elements. Here a resistor in the right direction with length L, and we can add a label 2 to the top. This time we add only one symbol. The other are blank, the other two. Now we are always at the relative position. We are now at the right side of the resistor. So you don't have to push this button every time. You can write some comments and see the result later. For instance, here's a capacitor in the down direction. And we had, for instance, a line. Line is a command in the PIC language. You can mix circuit macros and PIC language here. And the line is drawn from the bottom of the capacitor. If you want to draw it from the top, you can add a label and then specify it, and this line has to be drawn from this label. So then you can complete the circuit, close the circuit, adding, for instance, a gap, which is drawn in the down direction from this last point. C label is a label centered, so we can add here the output voltage. And finally, we want to close the circuit, drawing a line to the start of the graph. But well, we missed here the C, the label for the capacitor. So if you want to specify a line to the start, we have to define another label. So we go here, and we can declare a label. Here is always the actual position, and then we draw a line to start. Okay, so the graphic is of great quality, and you can save it and export it with the other button to the formats you want. And the format you want, you choose in the settings menu. Okay. Also, you have all the power of LaTeX to typeset formulas. So here you have a more complicated expression for your series for this label, and you save and export it. Okay, this is the idea. If you want to see how the command line works, so you have here some files, and we can activate the. Well, this is a thing that is necessary if you execute the PyCircuit in a Python inside a Python virtual environment. So the command line has all these options. You can process files and write the result in TXZ format, PDF, PNG, JPEG, SVG. You can specify the resolution of output raster images, the quality of lossy formats, destination directory, etc. So, for instance, here we specify, we call PyCircuit, and we ask for a PDF format, a PNG format with a dots per inch resolution of 250, and all the circuits ended in CKT. If this process encounters an error, you can choose to abort, to skip this file, to abort all the whole process, to skip this file, or to open the graphical user interface to see what's happening. So in this case, we choose the latter, and here's an unknown command. I put it on purpose. You can correct the error, save it pressing Ctrl+S or something, and the process follows. Okay, so that's in essential the working of PyCircuit. No? The future work here you have. I don't have much time to explain it, but it's self-explainable. And well, I would like to finish it the talk by showing you the relevant links of the project, and acknowledging the work of the many people that has preceded us to and wrote the software upon PyCircuit is based. Okay? Thank you very much.